Okay. I'm going to just give you a flat-out example of a mole fraction. Now, X is going to represent the fraction a substance is out of a whole. A is substance A. B is substance B. All you have to do is try to calculate, like I did yesterday. I combine Nick's weight, I combine David's weight together. They both weigh 300 pounds. I calculated how much David is of the total, and he's 48% or 0.48. That's what your answer is going to look like. It's going to be between 0 and 1.0. So David is 0.48 or 48%. Nick is 0.52 or 52%. So let's do an actual problem when it comes to mole fractions to try to make this as easy to understand as possible, okay? So what you do is, if I want to know what percent substance A is out of the total, here's X of A is going to be let me rephrase that. A divided by A plus B. And then X of B, wrong color, is going to be B divided by A plus B, or excuse me, yeah, A plus B. So here's an actual problem that's from your notes that we can use to apply mole fraction. And all you're doing is just finding out how much of the whole is a part of it. If I took Max's entire family, mom, dad, do you have any siblings? Mom, dad, and Max. And I want to know, okay, what percent of the three of them combined is dad's weight to the three of them? So I'm going to divide dad over the total family, and that will give me what percent dad is. So here we have, for HCl, we have 36 grams. For H2O, we have 64 grams. I want to know what is the molar mass, or excuse me, old habits die hard, the mole fraction of each substance. Well, the first thing you have to do is you guys are given these values in grams. Now, yesterday, Arshawn asked, well, if you put it in moles, is it going to be the same percentage? And I just, on reaction, I said, sure. But after thinking about it, no, you can't, because you can have 36 grams of a substance, but grams and moles are two totally different variables, two totally different units of measurement. So it's not going to assure that, you know, this is 100 right here. That's 100. But look at the elements that compose them. Chlorine is 35.5 grams per mole. And or hydrochloric acid is going to be about 36.5. Water is only 18. You have 64 grams of water, you have 18 moles, but then you have to extrapolate that and find out how many moles is 64 grams worth. So what you need to do first is convert the masses to moles. And so you will need to be looking at your periodic table. I would be a sadistic teacher if I never let you use your periodic table. So use your periodic table. We have 36 grams of hydrochloric acid. I pretty much have this one memorized, but I'll give you guys a moment to look at your periodic table. What is the molar mass of chlorine? 35.5. This is practice time. I want you all to get out your periodic table so you're ready for the real situation. Chlorine is 35.5. What is the molar mass of hydrogen? So we're going to have 36.5 grams per 1 mole. So this is going to be pretty close to 1. 36 divided by 36.5. Looks like we have 0.99 moles of HCl. Okay. And now let's do the 64 grams of water. I've asked you guys to just memorize this molar mass because you use it so much. Do you remember what the molar mass of water is? 18. Just memorize that. 64 divided by 18. Looks like we have 3.6 moles of H2O. Okay. And there you go. So I want you to find the sum. Looks like we have, 3.6 plus 0.99 is going to be 4.59. We're going to round it to 4.6. All right. Everything else should be a breeze now. So as I said earlier, X of A is going to be the mole fraction of hydrochloric acid. So you're going to do 0.99 divided by 4.6. Let's figure that out. That's going to equal about 22.22, which is 22%. Then X of B, that represents water. Looks like we have 3.6 divided by 4.6. Looks like we have 0.78. So out of 1 whole of water and hydrochloric acid in the amounts that we were given, about 78% of it is water. 22% of it is going to be the hydrochloric acid. This is how you do mole fractions. It's just doing the part over the whole. So an addition and then division. Yes. Well, if it were percent, we would say the actual percent symbol, but when it's like this, it's going to be in mole fraction. So you could say out of the whole, whatever fraction that will be, but leaving it in this format is fine. This is known as frequency, actually. It should be called mole frequency. The difference between frequency and percentage is actual saying 22%. Frequency is 0.22, when the total should be 1.0. So it should actually be called mole frequency, but I'm not the one that named it. All right, so we're halfway through the unit. All right, okay, let's go on to section 3. I want to show you guys a video if we get to it today. Unfortunately, my laptop I'm using thinks that YouTube is not connected to the internet, so I would have to switch over to this one. So that might be kind of a little trouble, but I want to show you some videos when it comes to this unit. We'll either do that today or we'll do that Monday. So section 3 is going to be factors that affect solvation. Now, I'm not saying salvation. You're not going to be saved. Solvation is solvability, like solubility, the ability to be dissolved. What can affect a solute's ability to actually be dissolved in a solvent? That's what we're going to talk about today and Monday. Did somebody say stirring? Yeah, that's one of them. It's called agitation. Okay, so let's talk about the solvation process. This is all about surrounding particles of solute with solvent particles. That is how you dissolve something. You have to get all the solvent particles to surround the solute particles. This is known as solvation. If you want to use a made-up word, that would be dissolvability, or the process of dissolving. So if you take a sugar cube that a lot of people use for coffee and you throw it into water and slowly it just starts to break apart, what's happening is the water is actually surrounding each little particle of sugar until it's all dissolved. Now, one thing to consider, and this is important when it comes to polarity, when considering polarity, polar and nonpolar, you must remember this. Like dissolves like. What that means is polar dissolves polar. It also means nonpolar dissolves nonpolar. But you will not get polar and nonpolar to mix. This is why oil spills are so messy. Polar and nonpolar do not mix. Have you guys ever heard of the spray called Goo Gone? It's a spray that gets rid of nonpolar substances. For instance, imagine that Derek breaks his window in his house this weekend, total accident, and you have to get a new window. Well, when you go to Home Depot or Lowe's to get a new window, there's this big manufacturer sticker on it. You have to peel off that sticker, and it leaves that big blob of glue. That glue is hydrophobic. It is nonpolar. If you get a sponge in water, it's not going to come off because water is polar. The glue is nonpolar. So you can get this stuff called Goo Gone. It's basically a nonpolar cleaner, and you spray it with a Goo Gone, you get a paper towel, it comes right off. Nonpolar will remove nonpolar, and polar will remove polar, but the two don't mix. So polar and nonpolar are insoluble with each other, so consider that. Polar and nonpolar, here's a new word, are insoluble. Actually, we did this word a few days ago, with each other. They just won't mix. Things like fat are nonpolar. This is why when you guys go to college soon enough and you're cooking something in the kitchen and you make a lot of fat, like let's say you're browning ground beef, makes a lot of fat, do not pour the fat down the drain because all that fat can clog up and the water will not remove it. So you pour all the fat like a jar or a glass and you dispose of it outside somewhere. But don't let big, huge cups of fat down the drain because that's going to be really tough to clean up because it's nonpolar. Okay, so let's talk about aqueous solution of ionic compounds. This is something I really have to teach my biology students about, my AP Bio kids about. So if any of you are going to be taking AP Bio next year, this is something big that I normally have to teach at the beginning of the year because they just don't get it. Okay, let's talk about sodium chloride. NaCl. This is an ionic compound. If you get down to it, it is composed of a positively charged sodium ion and a negatively charged chloride ion. Okay? This is table salt. Now, if I actually look at the ions, it's going to look like this. Here's Na. Here's Cl. A chloride ion is 36 or 35.5 grams per mole. Sodium is 23. So a chloride ion is a little bit bigger than a sodium ion. Now, I'm going to throw this into water. This is water. This is all going in. Here's what happens. Water molecules look like this. You hopefully remember this. There's oxygen, there's hydrogen, there's hydrogen. Now, think back to first semester. Water is polar. However, it has these things called partial charges. Hydrogen has a partial positive charge. Those little symbols I just drew are the lowercase Greek letter delta. And the oxygen has a negative charge, a partial negative charge actually. Okay, guys? Now, in this little cup of water, there are more water molecules than you could ever possibly hope to count. So let's just say there's innumerable numbers of water molecules. So I think you guys will understand this. The first thing that's going to happen is that the sodium and the chloride are going to separate from each other. So here's sodium, and here's chloride. They have now been separated. So here's where I think you're going to get it. What side of a water molecule would be attracted to the positively charged sodium ion? Would it be the partial negative oxygen or the partial positive hydrogen? Why would the partial negative oxygen be attracted to the positively charged sodium? Opposites attract when it comes to this. So here is what the oxygen, or excuse me, the sodium is going to look like. You ready? What's the bigger atom in a water molecule? Yeah. So what's happening here is that the partially negative oxygen is attracted to the sodium ion. Max, what is the partial charge of every oxygen atom in every water molecule ever? Okay, I just drew it over here, Max. This is oxygen. This is hydrogen. What is the partial charge of every oxygen atom in a water molecule? Negative. Just say negative. Here they are. Negative, negative, positive, positive. Tell me again, Max.
Negative.
One more time.
Negative.
What is the partial charge of a hydrogen ion, or excuse me, a hydrogen atom in every water molecule?
Positive.
Okay. Max, what is this charge right here on a sodium ion?
Positive.
What is attracted to positive?
Negative.
And so what side of a water molecule will always be attracted to a positive charge?
Oxygen.
That's right. And so if I draw it like this, there they all are. Okay. Kendall, what is the charge of that chloride ion? Negative is fine. What side of a water molecule would always be attracted to a negative charge like the one found here in chloride? So would it be the hydrogen side or the oxygen side? That's right. So we're going to draw these like this. Kayla, why are those water molecules attracted to the chlorine? Let me rephrase that. Why is the hydrogen atom side of the water molecules attracted to the negatively charged chloride ion? What is positive? And what is negative? Good. This is what affects solubility. What?
Because would the sodium be attracted to the oxygen because of like electronegativity? Or does that not matter?
No, it doesn't matter. This is just pure electrostatic attraction. That's what this is called. And let me put your description here. The partially positively charged, or the partial positive hydrogen atoms are attracted to the negatively, or we can just say the chloride ion. The chloride definitely has a negative charge. There's that charge right there. So this is just called electrostatic attraction. Positive is attracted to negative, and negative is attracted to positive. So I know that this is somewhat complicated at first, just like anything in life. So let's try one more example before I move on to the next topic. Let's say that I have a molecule of magnesium chloride. I'm going to throw it into water. Okay? It's going to first break apart. What will magnesium solvate into? That's the word. It's going to solvate. What ions will come out of this? We have MgCl2. What ions are there? Mg? How many? There's one magnesium ion, positive 2 charge. What else? 2 chlorides. Okay, I'm going to teach you guys something from AP Bio. This is technically not part of Chem, but I'm the AP Bio teacher here, and I deal with this a lot. Here's what I want you to tell me. Right now, magnesium chloride is 1 unit. Okay, that's all one thing. If you're going to take AP Bio, you need to know this. When you put something like magnesium chloride into water, how many units does it result in? 3. What we say is that its ionization constant is 3. Look at sodium chloride. How many units did it break apart into? 2. So its ionization constant is 2. Now, to kind of speed this along, we have 10 minutes left. What part of a water molecule would be attracted to the positively charged magnesium? Don't worry that it's positive too. That doesn't matter. Just positive is good enough. What part of a water molecule would be attracted to the positively charged magnesium ion? Would it be the hydrogen side, or would it be the chlorides, or the oxygen side? Carson? The oxygen side, positive to negative. Max, what part of a water molecule would be attracted to the negatively charged chloride ions? The hydrogen side or the oxygen side? That's it. That's it. Now I have one more for you. Hold on, Arshan. How about this? If I put glucose, this is important. This is a learning experience here. Right now, this is 1 unit. But let's see if you guys really know your stuff. Is glucose a molecule or is it an ion? It's a molecule. Now, some of you are like, huh? How do you know it's a molecule? How do you know it's a molecule? It's really big, sure. That's one. What's another one, or Kevin? Bingo. There's only nonmetals, carbon, hydrogen, oxygen. So here's the trick. Listen, try to make sense of this. Can a molecule have an ionization constant? No. So if it's 1 and I throw it into water, it's still going to be 1. And so its ionization constant is 1. It does not dissolve into its own little itty bitty atoms. So I'm just laying down this foundation because some of you are probably going to be my AP Bio students next year. And I know summer is going to be a long time, and then it'll be sometime next fall. But I'm just laying down those neural pathways now so we can dig it up later. Okay, but this is how things actually dissolve. Arshan, you're going to say something? Go ahead.
If there's a molecule that has oxygen and hydrogen, does it do anything different even though it's in water? Or is it still just...
It all stays as one unit. It won't really do anything. It's just like this. You said oxygen and hydrogen. You mean like a molecule that's just those two?
No, like if it's an ion, it's those two.
It's, well, something like hydroxide, like this.
Yeah.
It's going to be surrounded by water. It's going to be the oxygen side.
Okay.
Or actually, no, excuse me, the hydrogen side. It's going to look like that.
Why do the bonds break? Is it just they dissolve the bond slower?
Here's the thing is the ionic bond is what's holding the cation and the anion together. But when you're surrounded by something else, it's going to basically redirect those bonds to the solvent rather than to the individual ions. All right. Let's see if I want to do this one. Yeah, we'll skip that. All right. Let's do factors that affect solvation, like how things are actually dissolved. Arshan said this earlier. He said stirring. That's actually one of them. This is called agitation. What you want to do is you want to increase collisions between solute and solvent particles. So one of the ways that you can actually do this is stirring. Oops, where's my notes? There we are. So one method to increase those collisions is known as agitation. You shake it, you stir it, you mix it. So we have stirring and shaking. This is going to help you dissolve, or I should say, solvate solute particles more. Now, things will likely solvate. This just makes it go faster. So without agitation, solvation will be slower. I mean, it'll happen. You just want it to happen fast. Number 2, surface area. What do you think dissolves faster? A grain of sugar or a sugar cube? A grain of sugar, that's right. So smaller pieces are more soluble than larger pieces. Okay, now I want to give you guys a visual here to really help you understand how smaller pieces have a greater surface area. Imagine this. I have one little grain. I can have collisions all around it. As opposed to this. Water can only hit, like, let's focus on this one square right here. a solvent can only get one side, or maybe actually two sides. That's it. So there's less surface area when you have a cube of sugar because you're really only able to get maybe two sides, or if you're like this one here, you can only get one side. You know, a cube has 6 faces. Think about that. A cube has 6 faces. 4 around it, 1 on top, 1 on the bottom. But these individual units, you're only able to get 1 or 2 of the faces at a time. Whereas you have one cube here, one little grain actually, you can get all 6 faces at once if it's more smaller and dissolved. Yeah.
So is this referring to like a hydrogen ion versus like a francium ion as far as the size of one
It's the literal size of the solute that you're dissolving.
So like, are you talking about how many individual ions are in one?
No, I'm not talking about how many ions. I'm talking about literally, if you have a substance that you're going to dissolve, do you have it in its, like, are there a bunch of molecules together to form a larger polymer? Or do you have the individual molecules separated from each other so that you can dissolve it faster? Okay, and the last one I'm going to get to before you guys are dismissed, this will be a good way to end class today, is temperature. I think this one's pretty easy. Do solutes tend to dissolve faster when temperatures are hot or cold? Yes, but with a but. Typically, warmer temps dissolve solids faster. However, cooler temps dissolve gases faster. Think about those of you who like soda. Carbon dioxide is dissolved into the soda. When soda's flat, all the CO2 is gone. At what temperatures does soda get flat more? Warmer. So you got to keep a liquid cooler so that the gases can dissolve better. All right.